Welcome to DAR Tutors for online and home tuition. In this video, we will explore Gibbs energy change and its application to spontaneity and equilibrium. These are crucial topics for IB chemistry higher level. By the end of this session, you will be able to calculate Gibbs energy change, predict reaction spontaneity, determine the temperature at which spontaneity changes, and establish the relationship between Gibbs energy and the equilibrium constant. Let's begin by clarifying a common misconception. It's often mistakenly thought that an increase in entropy, which we represent as ds, always means an increase in temperature. This is incorrect. Entropy, a measure of disorder or randomness, is not solely dependent on temperature. A clear example that disproves this is a phase change, specifically boiling. A liquid boiling into a gas involves a significant increase in disorder. However, this phase change occurs at a constant temperature, the boiling point. So, we have an increase in entropy with no change in temperature, demonstrating that the two are not directly linked. This phenomenon was observed by Frederick Thomas Troughton, who noticed that the entropy change of vaporization was remarkably similar for many liquids at their boiling points. This observation is known as Troughton's rule. It states that the molar entropy of vaporization, ds vape, is approximately constant for many substances, with a value around 87 J per Kelvin per mole. Let's look at some data illustrating this rule. Methane has a ds vape of 83.0. Carbon tetrachloride is 5.8. Cyclohexane is 85.1, and hydrogen sulfide is 88.0. You can see these values are all very close to 87. Now notice water. Its ds vape is 109. Water is a notable exception to Troughton's rule. Why does water not obey the rule? This is due to its strong hydrogen bonds. These bonds result in a highly ordered liquid structure. When water vaporizes, this order is completely lost, leading to a much larger increase in entropy compared to other liquids. So, the entropy change is unusually high because the initial liquid state has a very low entropy. Now, let's move to a core concept that links enthalpy and entropy. This is the Gibbs energy change, denoted dG. It allows us to determine the spontaneity of a reaction using only the properties of the system itself, rather than the total entropy change of the universe. The fundamental equation is dG equals dH minus TBUS. This equation is given in Section 1 of the IB Chemistry Data Booklet and is essential for our calculations. Let's define the terms in this equation. dG is the Gibbs energy change. It represents the maximum amount of work that can be obtained from a system at constant temperature and pressure. The units are typically kilojoules per mole. VH is the enthalpy change. This is the heat energy change of the system at constant pressure, also in kilojoules per mole. T is the absolute temperature, which must always be in Kelvin. ds is the entropy change of the system. This is often provided in joules per Kelvin per mole. A critical point for IB calculations is unit consistency. The enthalpy and Gibbs energy changes are usually in kilojoules, while entropy is in joules. You must convert ds to kilojoules per Kelvin per mole. To do this, you multiply the entropy value by 10 to the power of -3, or simply divide by 1,000. This is a common place to make errors, so always double-check your units. The equation is often written with a deg symbol, dgdeg. This signifies standard conditions. 298 Kelvin, 100 kilopascals, and 1 mole per decimeter cubed concentration for solutions. It refers to the change in Gibbs energy when the reaction is hypothetically allowed to go to completion under these standard conditions. The real power of the Gibbs energy equation is its ability to predict spontaneity. Spontaneity in chemistry means a process that occurs without external energy input. The sign of the Gibbs energy change, dG, is the key indicator. A process is spontaneous if dG is negative. A negative dG corresponds to an increase in the entropy of the universe. If you see a negative dG, the reaction will happen on its own. A process is non-spontaneous if dG is positive. This means that to make the reaction happen, you must supply energy from an external source. Finally, when dG is exactly 0, the system is in a state of chemical equilibrium. The forward and reverse reaction rates are equal, and there is no net change in composition. Furthermore, dG represents the maximum amount of non-expansion work that can be obtained from a reaction. For instance, if a reaction has a dGdE of minus 237 kilojoules per mole, as in the formation of water, this energy can be harnessed to do useful work, like generating electricity in a fuel cell. This is why Gibbs energy is also known as free energy. It's the energy that is free and available to do work. Now let's work through an example to solidify our understanding. We will calculate the Gibbs energy change for the Haber process. We need to calculate dG for the reaction of nitrogen and hydrogen to form ammonia. First, let's write down the given data. The standard enthalpy change is minus 92.2 kilojoules per mole, and the standard entropy change is minus 199 joules per Kelvin per mole. Part A, calculation at 298 Kelvin. First, let's convert the entropy from joules to kilojoules. Minus 199 joules per Kelvin per mole becomes minus 0.199 kilojoules per Kelvin per mole. Next, we apply the Gibbs energy equation. dG equals dH minus TBUS. Plugging in our values, we get minus 92.2 minus the product of 298 and minus 0.19. This simplifies to minus 92.2 plus 59.3, which gives a final answer of minus 32.9 kilojoules per mole. The negative sign tells us the reaction is spontaneous at 298 Kelvin. Part B, calculation at 598 Kelvin. A useful approximation for IB chemistry is to assume that dH and ds values do not change with temperature, as long as there are no phase changes. For the Haber process, all species are gases at both 298 K and 598 K, so this assumption is valid. So we use the same dH and ds values and a temperature of 598 Kelvin. This simplifies to minus 92.2 plus 119, which gives a positive value of plus 26.8 kilojoules per mole. This positive result means the reaction is non-spontaneous at 598 Kelvin. Notice how increasing the temperature changed the reaction from spontaneous to non-spontaneous. This highlights the importance of the TUS term, especially at higher temperatures. Let's analyze the four possible combinations of enthalpy, delta H, and entropy, delta S, and how they determine spontaneity at different temperatures. Remember the equation delta G equals delta H minus T delta S. Case 1. Both delta H and delta S are positive. This is an endothermic reaction, delta H 0, with an increase in disorder, delta S 0. For delta G to be negative, the negative T delta S term must be larger in magnitude than the positive delta H term. This only happens at high temperatures. Case 2, delta H is positive and delta S is negative. This is an endothermic reaction that becomes more ordered. Delta H is positive, and minus T delta S is also positive because delta S is negative. Since both terms are positive, delta G will always be positive. The reaction is non-spontaneous at all temperatures. Case 3. Both delta H and delta S are negative. This is an exothermic reaction, delta H 0, that becomes more ordered, delta S 0. For delta G to be negative, the negative delta H term must be larger in magnitude than the positive minus T delta S term. This happens at low temperatures. Case 4. Delta H is negative and delta S is positive. This is an exothermic reaction with an increase in disorder. Delta H is negative, and minus T delta S is negative because delta S is positive. Since both terms are negative, delta G will always be negative. The reaction is spontaneous at all temperatures. Let's put this into practice with a calculation. We'll find the temperature at which a reaction changes from non-spontaneous to spontaneous. Consider the decomposition of calcium carbonate. This is the main reaction that occurs in a lime kiln to produce quicklime, calcium oxide. Here is the reaction and the given data. Notice that dH is positive and ds is positive. This falls into case 1 we just discussed, an endothermic reaction that produces more disorder. A gas is formed. This type of reaction is spontaneous at high temperatures. The question asks for the temperature at which it becomes spontaneous. This transition occurs at the point where dG equals 0. We can rearrange our equation, dG equals dH minus TBS, to solve for T when dG is 0. Setting dg to 0 gives TUS equals dH, which can be rearranged to T equals dH over ds. Now, we just need to substitute our values, remembering the unit conversion for entropy. Substituting 178 for dH and 164 for ds. But first converting ds to kilojoules per Kelvin per mole gives us 178 divided by 0.14. The calculation gives 1085 Kelvin. If we convert this to Celsius by subtracting 273, we get 812 degrees Celsius. This is the temperature, or more accurately, the temperature range at which calcium carbonate decomposition becomes thermodynamically favorable. For the reaction to proceed at a significant rate, an even higher temperature is typically used. We have successfully calculated the temperature at which spontaneity changes using the Gibbs equation. Understanding how temperature affects spontaneity can be visualized with a graph of Gibbs energy change, delta G, versus absolute temperature, T. This graph, which you should be familiar with for your IB exams, shows delta G on the y-axis and T on the x-axis. The spontaneity of a reaction is indicated by whether the graph is below the horizontal axis, delta G0 spontaneous, or above it, delta G0 non-spontaneous. The slope of each line on this graph is determined by the entropy change of the system, minus delta S. So, a positive delta S means a negative slope, and a negative delta S means a positive slope. Let's re-examine our 4 cases using this graph. For reactions with positive enthalpy and positive entropy, the graph is a downward-sloping line starting above 0. This line crosses the spontaneity threshold, delta G0, at a high temperature, becoming spontaneous. Our calcium carbonate example falls into this category. For reactions with negative enthalpy and negative entropy, the graph is an upward-sloping line starting below 0. This line also crosses the spontaneity threshold, but it becomes non-spontaneous at high temperatures. The Haber process is a classic example of this. And finally, reactions that are spontaneous at all temperatures have a negative enthalpy and a positive entropy. This results in a line that is always below 0. This visual representation perfectly summarizes how the balance between delta H and T delta S controls spontaneity across different temperatures. We have explored Gibbs energy and its link to spontaneity. Now let's connect Gibbs energy to chemical equilibrium. This will provide a deeper understanding of why reactions proceed to a certain extent. Remember, a process is spontaneous if dG is negative, non-spontaneous if dG is positive, and at equilibrium when dG is 0. Consider a simple reversible reaction between reactants A and products B. As this reaction proceeds, the total Gibbs energy of the system, represented by G, changes. If we start with pure reactants, the Gibbs energy is at a certain level. As the reaction begins to form products, the total Gibbs energy of the system decreases. This decrease is spontaneous. The reaction will continue to move in the direction that lowers the overall Gibbs energy. This continues until the system reaches a minimum point. What does this minimum represent? The minimum in the Gibbs energy curve corresponds to the point of maximum stability for the system. This point is equilibrium. The system will always spontaneously evolve towards this minimum Gibbs energy state, whether it starts with pure reactants or pure products. This is a fundamental principle of equilibrium thermodynamics. To recap, a negative dG for a reaction means it's spontaneous. This spontaneity drives the system towards equilibrium, which is the state of minimum Gibbs energy. This is a key insight for understanding equilibrium on a deeper thermodynamic level. Now let's explore the quantitative relationship between Gibbs energy change and the equilibrium constant, K. This is a critical equation you'll find in your IB data booklet. To do this, we need to distinguish between 2 related but distinct terms. First, we have the standard Gibbs energy change, dG-deg. As we've seen, this is a constant value for a given reaction at a specific temperature. It represents the Gibbs energy change if the reaction hypothetically went to completion under standard conditions. Second, we have the reaction Gibbs energy, dG. This value changes as the reaction proceeds. It tells you about the spontaneity of the reaction mixture at any given moment. It is the gradient of that Gibbs energy curve we just looked at. These 2 terms are linked by the following equation. dG equals dDEG plus RT log natural of Q. Here, R is the gas constant, T is the absolute temperature, and Q is the reaction quotient, which has the same form as K, but for non-equilibrium conditions. What happens at equilibrium? At equilibrium, the reaction Gibbs energy, dG, is 0, and the reaction quotient Q becomes the equilibrium constant K. Substituting these into our equation gives 0 equals Eg plus RT and K. Rearranging this, we get d equals minus RT ln K. This is one of the most important equations in chemical thermodynamics. This equation shows a direct quantitative relationship between the equilibrium position of a reaction, K, and the standard change in Gibbs energy, dG. Let's consider the implications. If dG is negative, then ln K must be positive, which means K is greater than 1. This corresponds to a reaction that proceeds largely to products. If dG is positive, then ln K must be negative, which means K is less than 1. This corresponds to a reaction that largely favors the reactants. Finally, if dG is 0, then K equals 1, and the equilibrium mixture contains roughly equal amounts of reactants and products. Notice that the units of dG in this equation must be in joules per mole, not kilojoules, because the gas constant R has units of joules. Pay close attention to this detail in your calculations. Let's apply the relationship dG equals minus RT ln K to a couple of worked examples. First, we will calculate the equilibrium constant for a reaction with a given dG. We're given the standard Gibbs energy change for this redox reaction at 298 Kelvin. The first step is to convert dG from kilojoules per mole to joules per mole, since R is in joules. So minus 9.08 kilojoules becomes minus 980 joules. This is a crucial conversion. Now we use our key equation and solve for ln K. We rearrange dG equals minus RT ln K to solve for ln K, which is dG divided by minus RT. Plugging in our values, minus 9080 divided by the product of minus 8.31 and 298. This calculates to 3.67. Finally, to find K, we take e to the power of 3.67. This gives an equilibrium constant of 39.1. Since K is greater than 1, we confirm what the negative dG already told us. The products are favored at equilibrium. Let's do a second example. This time, calculating dG from K and then dG from dG and Q. We'll work with the decomposition of dinitrogen tetroxide. Part A, calculate the standard Gibbs energy change, dG. We use the same equation, dG equals minus RT ln K. Substituting our values gives us minus 4,700 joules per mole. The positive sign is expected, as the equilibrium constant is less than 1, meaning reactants are favored. Part B, calculate the reaction. Gibbs energy, dG, when the reaction quotient Q is 0.1. Now we use the full equation. dG equals dD plus RT, L and Q. Plugging in our calculated dG and the given Q, we find that dG is minus 1,000 joules per mole. Because Q is 0.1, which is less than the equilibrium constant K of 0.15, the system is not yet at equilibrium and will spontaneously proceed in the forward direction to make more products, which is consistent with our negative dG. A final concept to understand is that non-spontaneous reactions can be made to occur through a process called coupling. This involves linking a non-spontaneous reaction, which has a positive dG to a spontaneous reaction with a larger negative dG. The spontaneous reaction provides the necessary energy to drive the non-spontaneous one. A simple analogy for this is a mechanical system. Imagine a pulley with two weights. Lifting the light weight is a non-spontaneous process. You have to do work on the system. However, if you attach a much heavier weight to the other side, that heavier weight falling spontaneously can lift the lighter one. The falling heavy weight provides the energy for the light weight to rise. This concept is vital in biology. Many life processes involve coupled reactions. For example, the synthesis of large molecules like proteins is often non-spontaneous. Our cells use the hydrolysis of adenosine triphosphate, or ATP. The hydrolysis of ATP is a highly spontaneous exothermic reaction with a large negative dG. Cells couple this reaction to non-spontaneous processes, using the energy from ATP to build molecules or move substances across membranes. This is how cells get work done. It is now time for some IB-style practice questions to test your understanding. Question 1. The reaction between hydrogen and fluorine to form hydrogen fluoride has a delta H standard of minus 542 kilojoules per mole and a delta S standard of minus 24 joules per Kelvin per mole. Predict the spontaneity of this reaction at low and high temperatures. Pause the video and try to solve it yourself. Here is the solution. This is a case where both delta H standard and delta S standard are negative. Such reactions are spontaneous at low temperatures and become non-spontaneous at high temperatures. The exothermic nature of the reaction, negative delta H, is the driving force. But as temperature increases, the unfavorable entropy term, negative delta S, becomes dominant and opposes spontaneity. To calculate the approximate transition temperature, we set delta G standard to 0 and solve for T. This gives us 22,583 Kelvin, which is an extremely high temperature. In a practical sense, this means the reaction is spontaneous under almost all achievable conditions, even though technically it would become non-spontaneous at temperatures above 22,583 Kelvin. Question 2. For a certain reaction, dG is equal to plus 2.50 kilojoules per mole at 298 Kelvin. Calculate the equilibrium constant K for this reaction. Pause here and attempt this calculation. Here's the solution. We use the equation dG equals minus RT ln K. First, convert dG to joules per mole, which is plus 2500. Substituting the values, we find that ln K is equal to minus 1.009. Taking e to this power gives us K equals 0.365. Question 3. The hydrogenation of ethene, C2H4 plus H2, forming C2H6, has a DHEG of minus 132 kilojoules per mole and a DESDEG of minus 121 joules per Kelvin per mole. Calculate the temperature at which this reaction becomes non-spontaneous. Pause and work through this problem. Here is the solution. Both DHD and DSD are negative, meaning it's spontaneous at low temperatures and becomes non-spontaneous at high temperatures. The transition occurs when dG is 0. Using the transition temperature equation T equals dHHdG over dsD, we substitute the values, remembering to convert dsD to kilojoules. The calculation gives a temperature of 1091 Kelvin. Below this temperature, the reaction is spontaneous, and above it, it is non-spontaneous. Question 4. Nitric oxide, NO, and oxygen, O2, react to form nitrogen dioxide, NO2. The standard Gibbs energy change for this reaction at 298 Kelvin is minus 71.2 kilojoules per mole. Calculate the standard cell potential, EDG cell, for the redox process at 298 Kelvin. This question links thermodynamics to electrochemistry. Take a moment to think about it. The key here is the relationship between dG and EDG cell, which is the Nernst equation at standard conditions. dG equals minus NF EDG cell. Here, N is the number of moles of electrons transferred, and F is Faraday's constant 96,485 coulombs per mole. To find N, we need to determine the oxidation states. In NO, nitrogen is plus 2. In NO2, it is plus 4. This is a change of plus 2 for each nitrogen atom. Since there are 2 nitrogen atoms in the balanced equation, a total of 4 moles of electrons are transferred. Therefore, N equals 4. Now we can solve for EDG cell. First, convert dG to joules. Rearrange to EDG cell equals minus dG over NF. Substituting the values, we get plus 0.185 volts. A positive EDG cell is consistent with the negative dG, both indicating a spontaneous reaction. Question 5. The standard Gibbs energy change for the formation of ozone, O3, from oxygen, O2, is plus 163 kilojoules per mole at 298 Kelvin. Calculate the equilibrium constant, K, for this process. This is our final practice question. Give it a try. Here's the solution. We use the same equation. dG equals minus RT ln K, and convert dG to joules, which is plus 163,000. Solving for ln K, we get a value of minus 65.717. Taking e to this power gives us an equilibrium constant of 8.9 times 10 to the power of negative 29. This is an extremely small number, indicating that the equilibrium lies very far to the left, favoring the reactants. This makes sense, as the positive digideg told us the formation of ozone is a non-spontaneous process. We have now covered the core concepts of Gibbs energy change, spontaneity, and equilibrium as required for IB chemistry CHEL. We've learned how to calculate dG, how to use it to predict if a reaction will occur, and how to find the temperature at which spontaneity can change. We also saw the vital connection between digideg and the equilibrium constant K, which quantifies the extent of a reaction. The practice questions demonstrated these principles in various contexts. Remember to always check your units and understand the meaning of the signs for dG, dH, and ds. For some students, these concepts can be quite challenging, especially at the higher level. If you are finding these topics or any other part of the IB, A-level, or IGCSE curriculum difficult, please feel free to contact our tutors. We provide expert online and home tuition to help you build confidence and achieve mastery. We're here to help you succeed. Thank you for watching, and we hope this video was helpful for your studies.